So now, what you can say is that since the Fermi energy is a so huge important reference level, it can be used in order to explain and or use in order to create model that can allow us to think about some problem in a more smart way. What does it mean? For instance, the Fermi energy, it could be really interesting in order to understand what is happening during the galvanic corrosion. What does it mean? So it's obvious that the Fermi energy is a measure about basically, for a certain point of view, looking about two different types of metal, how much the metals is enriched of electrons. And in particular, if you are coupling two metals, something like this, could be a more noble metal. For instance, it could be gold, and it could be a less noble metal. It could be, for instance, iron. So, what is happening is that we can appreciate coupling these two metals are forms of corrosion due to the movement of electrons from this metal to this one. And how it's possible? Well, it's in accordance with the Fermi energy, because iron has an higher Fermi energy with respect, for instance, gold. And so, obviously, a higher Fermi energy means a lower work function. But what is a work function? A work function is the work that should be done in order to remove one electron from one species, or one metal, for instance. And so since here we have a higher Fermi energy, and this corresponds to a smaller work function, we need to say that the system, when we are coupling two metals, try always to equilibrate the situations, trying to equilibrate the Fermi energy. But how it's possible to equilibrate the Fermi energy? Well, just increasing the number of electrons in one species, the smaller one, and at the same time decreasing the number of electrons in the other one. Because if we decrease the number of electrons in one metal, for instance, obviously the probability in each single energetics level of occupation decreases, because we have small number of electrons, and so the probability decreases. But at the same time, if we are enriching a second metal with further electrons, the probability for each single energetics level increase, and so the Fermi energy increase. And so we have a spontaneous flow of electrons in this way from a higher energy to a lower energy. So the Fermi energy is an extremely important tool that allows us to understand why we have certain types of phenomena and why we have a certain flow of electrons. This is extremely important, for instance, in galvanic corrosion, the corrosions that occurs when you are coupling two metals. But what is the relationship between Fermi energy and the polarization? So, let's imagine to have one electrode. Again, this is our electrode in a solution. So, we have our electrode and a solution. We have an electrode and a solution interface. So, electrode and solution. Basically, what is happening here is that on this electron we have a certain connected semi-reaction. So the semi-reaction is basically an oxidation of one species or the corresponding reduction. So it could be a metal, for instance, chopper oxidations and corresponding reductions and so on. One classic example, it could be something like this. So we have our maybe chopper, and we have some chopper 2+ in solution. So this is metallic chopper, and this is chopper 2+. And so we have, for instance, this oxidation, if the reaction is proceeding in these directions, collecting metallic chopper from cations, or maybe the opposite, releasing cations due to the oxidations of metallic chopper. And so the reaction is proceeding in the opposite direction. So basically, what is interesting here is that in the moment in which we are polarizing the electrode, so with a potentiometer, we are inducing a current due to a potential difference. We can polarize it negatively. So basically, we can induce a negative charge. Or maybe, if we are doing the opposite thing, so we are promoting the flow of electron in the opposite direction, we can improve the formation of positive charge. And so we are positively polarizing the electrode. Basically, obviously, if you are polarizing positively this electrode, the counter one should be polarizing negatively and the opposite, in accordance with what we have described during the previous lesson. But what is important here is that in the moment in which we are, for instance, polarizing negatively this electron, what we are doing is introduce electron in the system, electron in the metal. But if we increase the electron in the metal, we are increasing the Fermi energy. Why? Because we are filling the previously empty state for each single energetics level. And so maybe the state, if we want to describe this with an imaging, we can say that again we have our well-known energetics level and the corresponding amount of energy density. So basically we have this energetics level that is completely occupied. This is maybe occupied in this way, and this is the Fermi energy of occupation, and this one. What is happening basically, now the third level in this example is the Fermi energy. So we have E1, E2, and E3 is the Fermi energy, and E4, when a probability even smaller. If we are inducing electrons inside with a potentiometer, we are negatively polarizing, we are increasing, for instance, the number of electrons, and so what is happening is that we are filling maybe this state, we are increasing the number of electrons here, and so since we are adding electron, now what is happening? That the Fermi energy is not anymore this one, but is higher, is this one. And so negatively polarizing, what we are doing is increasing the Fermi energy. So for a negative polarization, we are increasing the Fermi energy. But if we are increasing this Fermi energy up on a value that is higher with respect to the lowest unoccupied molecular orbital of the oxidized species in solution, we have spontaneous flowings of electrons in this way. So the reactions proceed in this way toward an oxidation, because the electrons that are arriving here are used in order to reduce this one. Because always electrons try to follow a configuration in which the energy is smaller, the voltage is higher, but the energy is smaller. And so if we want, from the other hand, induce a positive polarization, so promoting the exclusions of electrons, we are doing the opposite, so we are decreasing the number of electrons, and maybe now the Fermi energy is A2. And so we are moving the Fermi energy here, but if we reach a value in which the Fermi energy is smaller than the highest occupied molecular orbital, we have the flowing of electrons in this way. And so the elimination of one electron from here, and the oxidations of metallic chopper, for instance. And so we have that these electrons asking from here promote the formations of an oxidized species. And this is the link between the Fermi energy and the polarizations in electrochemistry.